As you have heard, my name is Oliver Cencic. I'm working here at the Vienna University of Technology since 2001, and we started to develop the software Stan that you are going to work with after my lecture in 2004. The first version of Stan was then released in 2006, and now I think a few weeks ago we released the latest version of Stan, and I think you are going to work with this version. Anyway, before you are working with Stan, you need to know a few basics that are essential to know what Stan is doing for you or what is happening in the background of Stan. And that's the reason why I'm here today. Yuka told me that he has already covered the basics of MFA in one of his last lectures, so I will only go briefly through them again, and I will focus mostly on the mathematics and the statistics that you need to know. But you don't have to be worried. It will not be, it will not be hardcore mathematics or statistics. So every one of you will be able to follow me, I hope. Okay. I will go through these slides. Yeah, what is material flow analysis? I think you've heard it in the last lectures. So the goal of material flow analysis is to model flows and stocks of a system that you are interested in with respect to goods and substances. So you have to quantify the goods and substances inside of your model. And the most important constraint when you're doing material flow analysis is that you have to obey the law of mass conservation. So material cannot appear or disappear within your system. So there has to be a conservation law. So everything that is going into a process must come out again. I think you have already seen how such an MFA model looks like. You have a system boundary, you have processes within the system boundary. Of course, there are also some outside, but they are not of interest for us. For us, only interesting is everything that is inside of the system boundary. These processes can contain stocks, so there is a chance that material is accumulated or depleted. And these processes are connected by flows. These are internal flows. And of course, they can also cross the system boundary. So then they are called import or export flows. I think this is more or less clear. So this is your graphical model, the modeling in space, let's say it in this way. And the next step is that you have to model in time. That means that you have to decide which period of time you're looking at, 1 year, 1 month, an hour, and you have to try to collect the data for this time period. When you succeed in collecting your data, your model will look like, so each of these oval shapes will have some numbers in it. And what is here important is, of course, you have to have some legend telling the people what these numbers mean. One question from my side, can you see my mouse pointer moving?
Yes.
Okay, perfect. All right, so that's the goal of MFA. You have to quantify all of the flows and stocks inside of your model. The next thing is that has already been covered, the difference between goods and substances. Only very briefly. So a good is something that you can take into your hands, that you can deal with, that has some value. Let's say it can be waste, or it can be a car, or it can be anything else. And inside of these goods, there are substances. Substances are elements of the periodic table or compounds. That depends what you want to focus on in your MFA. So what you see here is a small MFA model with one flow going in, two flows going out. And this input flow is split up into two flows. You see the 60 mass units going in are going 24 to flow 2 and 36 to flow 3. Within these goods, there are substances. Let's say I'm interested into the green and the red substances, and the rest of the substances are not of interest for me. So I've displayed these substances as green and red squares here on the left side. And when these substances are going through our model, it can be that these substances are distributed in a different ratio than the flow of goods themselves. So you see most of the red substances has 2, while none of them were going into flow 3. And the green substances, most of them were going to flow 3 and a few of them to flow 2. And the only thing that you have to do now to go from, or to make the step from an analysis on the layer of goods to the layer of substances is you have to count, let's say here, the red squares. So there are 10 squares going in and 10 squares going out and none going to flow 3. And of course you can do the same for the green substances. Normally you do not have the information about the mass flows of a substance inside of a flow. What you have normally are some substance concentrations that you get from some analysis from laboratories and so on. So the link between the layer of goods and the layer of substances is via these concentrations. So again, the law of mass conservation, when we are looking at different time periods, again a small example, you have here a process where 100 mass units are going in and 80 mass units going out. As I've told you before, we have this law of mass conservation. That means material cannot disappear. When there is less material coming out of a process than it going in, the difference between these two flows must have gone to the process stock. So you see, we have here a raise in stock of 20 mass units. So that's again mass balance. And now when you're looking at another period that is directly attached to the first one, of course you can use these two numbers that were given here. So the amount of material inside of your stock at the beginning of period 1 plus the change in stock in this period tells you how much material there is in period 2 at the beginning of period 2 inside of your stock. Here you can have, of course, different mass flows. Again, the difference of these two flows is going to your stock, and you can use these two information or these two numbers to again calculate the material inside of your stock at the beginning of period 3. So what kind of or what types of equations are we using? So first of all, we have a balance equation that I've already mentioned. So everything that is going in must come out again, with the only exception of a stock. So sum of inputs equals sum of outputs plus the change in stock. The second equation is this stock equation that I've already mentioned. So the amount of material inside of your stock at a certain period is the amount of material inside of this stock in the previous period plus the change of stock inside, the change of stock in the previous period. Most important part here, mass conservation. So materials cannot appear or disappear. This is really, really important. Then inside of STEN we are using some linear relations. The first of them is called a transfer coefficient equation. I'm pretty sure that Yuka has mentioned what a transfer coefficient is, but just to cover it briefly, transfer coefficient tells you how much of the material that is going into a process is going to a special output. So the output flow is the amount of material going into this process times a transfer coefficient. So the second thing here is not that important. And what I've already covered are these concentrations equations. So telling you how much the mass of a substance is the mass of good times a concentration. So that's the connection between the layer of substance and the layer of a good. Here, this concentration of a substance. We have different ways to cover these concentrations in STEN, but that's not so important here. Okay, now let's consider we have created a small graphical model, and of course before being able to make any calculations, STEN has to translate this graphical model into a mathematical model. And I think it's pretty easy to understand what is going on. Let's have a look at it. So we have here a small model with two processes. Here's one flow called raw materials going in. And then we have something here like a recycling flow. These two flows are combined into a product. This product is used, and a certain amount of this product is going back as recycling material. It is defined by this transfer coefficient, and the rest of the material that is not reused is disposed of as waste. So now how to describe this model in a mathematical way? We need three equations to do this. The first is the mass balance of process production. So raw materials plus recycling material equals product. This is this equation. The second is the product flow equals the waste flow plus the recycling material flow. That's the second equation. And the third equation is a transfer coefficient equation telling you that a certain amount of the product that is going in is going back as recycling material. So you see recycling material equals the product flow times the recycling rate. So we have now three equations describing our system or model completely. And if you count the variables that are involved here, you see that we have 5 variables. And I'm pretty sure that all of you know from school or university that it is not possible to solve a system of equations that look like this. So when you have 3 equations and 5 variables, you need to know at least 2 of them to be able to solve this system completely. And we call this choice of the parameters a control basis. So now let's assume we have data for the product flow and the recycling rate. One question that pops up often here is, okay, when I have 5 variables and I can choose which of them I want to measure, my recommendation is, of course, to take those variables that you can measure the easiest and where you get the most precise data for, so where the uncertainty is the smallest. But let's assume we have data about the product flow and the recycling rate. The only thing that is need to be done is to transform this equation system that all of the unknown variables are expressed as functions of these 2 given parameters. I'm pretty sure each of you can do this, so you have to transform these equations. And you see now that these unknown variables, recycling rate, raw materials, and waste, are now expressed as a function of the recycling rate and the product flow only. So if you know the numbers for recycling rate and product flow, you can calculate the rest. Okay, so now I'm coming to the most important part of my presentation, and I want to give you a small example telling you what it's all about. So let's assume that you have to compare 2 technologies, let's call them A and B, and that can be expressed by a single parameter. And we want to choose the technology where this parameter is the lowest. So when you have now data for technology A and B, and you have a look at these bars, you might probably say that technology A, here is the parameter the smallest, so this is the better one. But you have to be careful. When doing such comparison, you have to take into account the uncertainty of the data. So it could be that the parameter is not precisely defined, but there is some uncertainty range. And if you have such uncertainty ranges, in this case here, we have here a region between these 2 ranges where these 2 uncertainty ranges are not overlapping. So in a statistical sense, you can say that the parameter A is here definitely smaller than parameter B. But it can also look completely different. Let's say the uncertainty ranges are much, much larger. And now you see that here is an area where these uncertainty ranges are overlapping. And that means no statistical test would tell you here that parameter or that technology A is better than technology B because of these overlapping uncertainty ranges. So my credo in this respect is that whenever you are collecting data, you have also to consider the uncertainty of this data. So a stated value without an uncertainty is in my opinion more or less worthless. Only when you know the uncertainty, you have the possibility to compare this data and to perform some, let's say, some sensitivity analysis. And of course, when you state this uncertainty, it must be clear what this uncertainty means. Is it a standard uncertainty, the standard deviation? Is it some kind of extended uncertainty? You have it to make it clear in your report that you are writing. Okay, well, what is data uncertainty? you might know this guy on this picture here. It's Carl Friedrich Gauss. He's one of the most known mathematicians. He lived in Germany around 1800, and he worked a lot with uncertainties. And he was the one who invented or who discovered this so-called standard deviation. I'm pretty sure that you have seen this formula before. So he said whenever you're taking a sample from a population, you take the individual elements of this sample, sum the values up, and divide it by the number of samples to get a mean value. And then you can use this formula to calculate something that is called the standard deviation. So this is the deviation of the individual sample species from the mean value. And he also discovered that most of these distributions where you are collecting a lot of data following a normal distribution, you might know this bell-shaped curve that you see here on this picture. It was on the old 10 mark, on the old 10 mark bill in Germany before the euro swept over Europe. Okay, and one additional thing that you need to know is a term that is called standard uncertainty or standard error. This is something completely different to the standard deviation that I mentioned above. So you need to know that these two parameters that I mentioned above are parameters that describe the sample distribution. So you are sampling a population, and these two parameters describe the mean value and the standard deviation of the individual elements of the sample. But normally we're not interested into this sample. We want to have an estimator of the population, the whole population that we are sampling. And therefore you need this term standard uncertainty. It's more or less the standard deviation divided by the square root of the numbers of the sample size. This sounds a little bit difficult, but it is not. I will give you a small example that I created. Okay, let's say you want to get a number of the copper ore, of the concentration of the copper ore inside of this mountain. I think for each of you, it is clear that you cannot analyze the complete mountain. You cannot cut it into pieces and analyze any of these samples. You have to take a smaller sample. So let's say we're taking a sample of size 10, so the 10 individual samples from this mountain, and we give them to a laboratory and ask them to analyze the copper content inside of each of these elements. So we get 10 different copper concentrations. The next thing that we are doing is we are computing the mean value of this sample with the formula that I showed on the previous slide and the standard deviation of these copper samples. So you get more or less a picture of the mean value of this sample, and you get a picture how much these individual values deviate from the mean value. But we are not interested into the mean value of the copper sample. What we want to know is the copper concentration inside of the ore. But unfortunately, we have no better values than the ones that we got from our sample. So what we do is we take the mean value of the sample as the best estimator for the copper concentration inside of our mountain. We do not have any better values. And the next thing that we have to do is we want to know the uncertainty of this estimator. And for that reason, you need to use this uncertainty that I showed you before, this one here, the standard uncertainty. So you take the standard deviation that you have calculated and divide it by the square root of n. And then you get a number. And this is the uncertainty of the estimator of the copper ore concentration inside of our mountain. Okay? So now something that you might think about is if we would be able to analyze the complete mountain, it should be more or less clear, assuming that there are no measurement errors, that we could determine the copper concentration of the ore precisely. So just to think about it, let's say we want to know the uncertainty of this mean value that we computed here. So we are taking into account only this sample here. So What should be clear is that because now this sample is our complete population, and we have analyzed the copper concentration in each of these individual elements, the uncertainty of our sample, of this estimator here, should be 0. And if you're only considering this standard uncertainty that I mentioned before, you would get more or less the same value that you have here. But the difference between these two things is that in the first case, we have a more or less infinite population. So the mountain is consisting of, let's say, infinite small samples. But here you have considered the complete population, and the population is here, the sample size is only 10. And in this case, you have to use something that is called the finite population correction term. That's that part here, to get what I've already told you, that the uncertainty of this copper concentration of this sample is 0. But this part is not so important for you, only to make it clear once. I think each of you knows how a normal distribution looks like. It's this bell-shaped curve. In the middle, you have the mean value. And when you go from the mean value to the left side and the right side, 1 times the standard deviation, you get here an area that covers 68% of the possible values of a probability of the probability density function of the normal distribution. If you enlarge this region to approximately 2 times the standard deviation, you already cover 95% of the normal distribution. Just keep this in mind, please. We need it later. Okay, how do you get the uncertainties that you have to use in STAN? The best case would be if you have a series of measurements that you can evaluate statistically, like I've shown you before. So you are computing the mean value, you are computing the standard deviation, and then you're computing the standard uncertainty. But often you do not have a series of measurements, and then you have to try to figure out the uncertainty in other ways. And one might be to use some, let's say, calibration certificates of your measurement device, or you have experience from past experiments, how large the uncertainty is. Or if none of these values are available, then you can also use common sense. So you make an educated guess how big the uncertainty is. An educated guess is definitely better than assuming that there is no uncertainty at all, because that's definitely not the case. Okay, but the thing is that when you are making such educated guesses, normally when, let's say, we were asking an expert for a number of, I don't know, the amount of waste in Austria in the year 2016. And he might estimate, okay, it is not smaller than A, and it is not larger than B, because he has no preference which of these values in between A and B is better. We would model this educated guess with a uniform distribution that looks like this. But inside of STAN, you have to type in the uncertainties in form of normal distribution. That's essential. That means it's independent what distribution function you are assuming here. You have to transform it into a normal distribution that is best fitting this, for example here, uniform distribution. It could look like this. So when you open one of your statistical handbooks or you look in Wikipedia on the internet, you will find for most of the distributions that you can think of, the mean value and the standard deviation. For a uniform distribution, it looks like this. And when you now take these parameters, the mean value and the standard deviation that has been calculated for the uniform distribution, and you assume them to be the parameters of a normal distribution, and you draw them in the same graph, you see that the normal distribution looks like this. So it covers most of the area of this uniform distribution, but of course, it must be clear to you that there is also a possibility that there are some numbers outside of this uniform distribution, because the normal distribution is going to infinity in the negative in the positive area. But anyway, we need to have this normal distribution in order to use the algorithms that are implemented in STAN. This is data reconciliation and error propagation, so there is no other way than transforming it into a normal distribution. Okay, I've already mentioned error propagation. What is this? Let's assume that you have a function. You have here y that is a function of some measured parameters. And so you need you know the distribution of x1 and x2, and you are combining them inside of a function. Because each of these measurements here has an uncertainty, it should be more or less clear that also the result of this function has an uncertainty. And that's what can be calculated with error propagation. Here is the formula. I do not want to go into detail here. And it's called the Gauss law of error propagation. On the next slide that I think you get the handouts later, I've mentioned here a few the results of a few of the basic calculation rules, plus, minus, multiplication, division, what the result of error propagation looks like. And to give you a small impression how this formula works, I have created or have prepared another example. Let's say we have here a function. F is a function of a, b, c, d, and that's the function a plus 2b plus c times d. And now we want to compute the uncertainty of f, assuming that each of these parameters has an uncertainty. So the best estimate of the mean value of f is when you insert the mean values of a, b, c, and d into this formula. So that's our best estimator for f. And now we want to compute the uncertainty of this parameter by using the law of error propagation. So it looks pretty complicated, but it is not. The only thing that you have to do is you have to derive this function with the partial derivation of this function with respect to each of these variables. So if you derive this function with respect to a, you get df by dA is 1. The partial derivation of f with respect to b, it's 2. The partial derivation of f with respect to c, it's d. And with respect to d, it is c. And the only thing that you need to do now is you take these computed values and multiply it with the square of the standard deviation of the variable. So that means 1 squared times SA squared plus 2 squared times SB squared plus D squared plus C squared times SD squared. And that's the result that you get. But you do not have, it's only for you that you get an impression what error propagation is about. Stan is doing everything that you see here for you more or less automatically. So you only have to enter the uncertainties of your input parameter and you will get the result of the uncertainty of the results automatically. Here we have a small model. So to show you what is going on. So you have, let's say, two flows going in. 10 plus minus 2, 50 plus minus 5. And when we want to know the mean value and the uncertainty of flow C, everything that is done is, okay, the mean value of C is computed by adding up the mean value of A and B. And the uncertainty of C is computed with the law of error propagation that I've showed you in the previous slide. Okay, now we are here. That's the most important part of my presentation. It's about data reconciliation. So what is data reconciliation about? It was also invented by Carl Friedrich Gauss, and it is based on something that is called the method of least squares. So you might have heard about it. So when you have a data cloud, or let's say data points that represent x and y values, you can print something like a cloud of points inside of an XY diagram. And the question during this method of least squares is we want to find a straight line that is best representing these values. So it is not completely clear how the position or how the where this straight line lies. And what is done here with the method of least squares is you are taking the distance from the point to this line, you square the distance and you sum them up, and then you get a number. And when you now assume a different line, you will get a different number. And the method of least squares say that the line is the best where the number that we have calculated is the least. So that's the method of least squares, and that's the basis of data reconciliation. But that's not so important for you. What I want you to take from this lesson is why we need data reconciliation and what is going on during data reconciliation. So have a look at this small example. So you see we have a process where 100 mass units are going in and 110 mass units are going out. As I've told you before, we have a problem here because the law of mass conservation, it's not fulfilled. We have a conflict. There is 100 going in and 110 going out. So that's something that is not possible. There is an error inside. But the good news is we can solve these problems if we have something that is called an overdetermined system of equations. That means you have more equations than unknown variables. So here we would have one equation telling us about the mass balance of process 1, import equals export, and when we can assign some uncertainties to these data to the data that we have collected. Okay, let's assume that's more or less the same. It is the same model, but this time we have computed, or we have data about the uncertainty of the export flow. So the question now is it possible to perform data reconciliation? So we have to check these two requirements. First of all, is it an overdetermined system of equations? Yes. We still have this one equation, the mass balance, and we still have no unknown value. So we have one equation, no unknown value. That's an overdetermined system of equations. And now we have uncertain data given. So it should be possible to perform data reconciliation. What is happening is now the following. Data reconciliation means that the values with an uncertainty are adjusted in a statistical sense that afterwards the contradiction of the data is gone. So what you see here is that after data reconciliation, the value that we have that was given for the export flow has been reduced to precisely 100 plus minus an uncertainty of 0. So now these two values are completely the same. And I think this is more or less obvious that it should be the solution because the import flow has no uncertainty, so it cannot be changed in any way. So the only data that you have collected and that is possible to be changed is this export flow value, and it has to be, after data reconciliation, exactly the same number like the import flow. Okay, now we have the same model, and this time the import flow and the export flow has an uncertainty given. So the question now is, what is the result now? Okay, and yeah, because I cannot see you here, and normally this would be an interactive part in my presentation where I let the people guess what the result of this example is, but I will show you the results here. After data reconciliation, the mean values are adjusted to be exactly the same. And an additional feature of data reconciliation is that the uncertainty that is originally given has been reduced. So the question now is why the result is exactly 105. And I think this should be more or less obvious. I hope you can see my picture, so I will try to show you here. So you have 100 on this side and you have 110 on this side. Both of these measurements have an uncertainty plus minus 10. That means they can be shifted with the same extent. So whenever one of these values is shifted, the other one is shifted in the same extent. And they have to meet somewhere. If you move them, the only position where they can meet is exactly in the middle between 100 and 110. That's the reason why the result is 105. So now let's take this. Yeah, the reason why this is so is written here, but it's not important for you. It is in this small simple case of two measurements and only one process, it's more or less the weighted mean, and you could use these formulas to compute the results yourself. But I would like to give you another example. So this time we have both of the measurements have an uncertainty, but this time the import flow has an uncertainty of plus minus 5. and the export flow an uncertainty of plus minus 10. And the question now is, what is the result now? And if you perform data reconciliation, you will see that now the result lies much closer to the value of the import flow, is 102. And again, I think it's more or less clear. You have 100 here, you have 110 here, and this time 100 has a small uncertainty. So that means whenever you're moving this 100 to a small extent, 110 is moving to a larger extent. So it looks like more or less like this. And where are they meeting? Yeah, in the region near 100. So the precise solution is this 102. And again, you see that the originally given uncertainty has been reduced. So these are the two most important features. Conflicting data will be resoluted, so there is no conflict afterwards, and the uncertainty of the original given data is reduced during data reconciliation. Okay, now let's have a look at this example. Now you see we have the same model, and this time you have an uncertainty, the uncertainty is the same, but this time you have the import flow 1000 and the export flow 100. It should be more or less clear that here something happened during entering of data, so there is an error included in this model. So either this import flow is only 100 or the export flow is 1000. So there is 10 too much or too less. So when you perform data reconciliation now, and that's a question that I normally ask my audience, is do you think that it is possible to reconcile this data? And I often get the answer no, because these values are not fitting. But that's not true. In a mathematical sense, you will get a result, of course, that is lying precisely between 100 and 1000, because the uncertainties of these two measurements have been the same. So it's 550 plus minus 7. But of course, in a physical way, it doesn't make any sense because there was an error included. And to find out these kind of problems, we have implemented in STAN a statistical test that looks like this. So let's assume this is the original given data, and after data reconciliation, you might get a value that lies here. If this value is lying into this region that I mentioned before, approximately 2 times the standard deviation, this 95% confidence interval, Stan will tell you that this reconciled data is more or less okay. It's plausible. But whenever you get a value that is lying outside of this interval, you will get the message that inside of your model there is a problem with data. So you have to recheck the data and try to find out where the problem is situated. Okay, now a little larger example. So this time we have one process with 2 import and 2 export flows. And the problem that we have here, when you look only at the mean values of these flows, we have 300 mass units going in and 280 mass units going out. So there is a conflict in data. The values are not fitting to each other. And the question is, can we perform data reconciliation? Again, we have to check, do we have an overdetermined system of equations? We have one mass balance, this means one equation, and we have no unknown value. So that means overdetermined system of equations, check. The next thing, do we have uncertain data? Yes, of course. Each of these values has an uncertainty, so it should be possible to perform data reconciliation. So if you enter this data into STAN and perform the calculation, you will get these results. So when you sum up now the reconciled values of the import flows and the export flows, you will get exactly the same number. It's 290. And again, you see that the uncertainties of the originally given flows has been reduced. Okay, now remember we have here the same absolute uncertainty for all of the flows. But what happens if these flows, they have the same mean values here, have different uncertainties? From what I've told you till now, it should be clear that when we perform data reconciliation and the original given number has no uncertainty, it must be the same after data reconciliation. So it is not possible to adjust this value. And when you look at the import flow, it has an uncertainty of plus minus 5. And the export flows have, after data reconciliation, this value has been adjusted only to a smaller extent. And these two values should have been adjusted to a larger extent. And that's exactly what we get after data reconciliation. You see, the values are again fitting. When you sum up the import flows, you get 297.8, and that's exactly the same number when you sum up the export flows. Again, the uncertainties have been reduced. But be careful. When you look at these numbers and the numbers before, the only difference between this model and this model was the uncertainty that we have entered into our system. And the results that you get are completely different. So the results of your data reconciliation, of your analysis, depends heavily on the uncertainty that you assign to your numbers. So you have to take care that you determine the uncertainties of your numbers in the best way possible. Okay, and here a last example. This time we have a larger model, two processes, process 1, process 2. And the difference now is that we have here on flow. The question now is, again, why do we have a problem here? Let's say it in this way. If you build the mass balance of process 1, it should be clear that there should be 220 mass units entering from below so that the mass balance is fulfilled. If you do the same with process 2, you will see that 210 mass units should leave process 2 in order to fulfill this mass balance. And unfortunately, the flow leaving process 2 is going into process 1, and now we have two different numbers and we are not sure which of them to use. Data reconciliation offers you a possibility to solve these kind of problems. And the only thing that you have to do is to check if the two requirements are fulfilled. First of all, do we have an overdetermined system of equations? So what do? We count the balances or the equations that are necessary to describe this model completely. This is the mass balance of process 1 and the mass balance of process 2. So we have two equations and we have one unknown flow. So we have more equations than unknown flows. That means the first requirement is fulfilled, check. And the second requirement, we need to have uncertain data. I think, okay, also fulfilled, perfect. Now, if you press the calculate button in STAN, you will get the following result. So we'll see that the numbers that are written red here have been reconciled. But it's more or less a strange thing why this number here in the middle, the product flow, has not been reconciled. So the number is staying the same. And the reason for this behavior is something that is going on inside of STAN. What Stan does is he takes all the equations that he can set up for this graphical model and tries to eliminate these unknown flows from these equations. And in this simple example, this happens when you add the two equations for process 1 and process 2. You will get an equation that describes the mass balance of this big process that you see here. So you add these two equations and you get the balance equation of this large process. And now we have the same situation like before. We have one process. We have all the data that is going in and out given. And now we can perform data reconciliation. And that's the reason why only these three values have been changed and the value in the middle not. And as soon as the contradicting values have been reconciled, you can use the results to compute the precise value of the unknown flow together with its uncertainty by using error propagation. Okay, to sum it up, what's the difference between error propagation and data reconciliation? Let's start with error propagation. In error propagation, you have to have an exactly determined system of equations. That means you have to have the same number of equations as unknown flows. So we have here one process, that means one balance equation and one unknown flow. So we have an exactly determined system of equations. and we have uncertain data given. If these requirements are fulfilled, we can compute the uncertainty and the mean value of flow 3 by error propagation, and that's the result. But you also should be aware of that the original given data are not changed during error propagation. The only thing that you get is the mean value and the uncertainty of the unknown flows. On the other hand, we have data reconciliation. Here we have something that is called an overdetermined system of equations. That means you have more information that is normally necessary. So when you have one balance equation, it could be used to compute one of these flows that are going in and out. Because all of them are given, we have something like, let's say, redundant information. And this redundant information can be used to adjust these values in a statistical sense. So after data reconciliation, you see that the mean values have been adjusted and the uncertainty has been reduced. So that's the difference between error propagation and data reconciliation. Okay, when you want to have more information about MFA, STAN, and data uncertainties, I recommend this book here at the end of the first row. It's the Handbook of Material Flow Analysis. It was published in December 2016, and two of the chapters inside were written by myself. One of them is covering this uncertainty topic, and the other one is presenting 3 examples that have been done by STAN. What you can also do is you can visit our website. It's www.stan2web.net. And here you find a lot of information about STAN. You find a help video that I would recommend you to have a look at. It's approximately 20 minutes. And here you can also download our software when you have registered once. Yeah, that's our software. Here again, the link to our software. And just to cover it briefly, a few facts about STAN. First of all, STAN is freeware, so you can use it for free without having to pay anything for it. We have spent so far nearly 400,000 euros into the development of STAN. It was released first in 2006, and till today we have nearly 13,500 users that are using STAN worldwide. So really a huge community by now. Okay, I think I'm at the end of my presentation because 45 minutes are gone. Inside of your slides, you will find a few additional information why we used or why we created the software. And what you also will see is some screen prints of the software themselves. But I'm pretty sure that Jukka will present STAN now to you and that you have the chance to practice to use STAN during your exercises. Okay, so far that's all from my side. I wish you fun with your exercise. And yeah, do you have any questions that I can answer?
Any? Oliver, could you just briefly show the STAN portal? Because
yes,
it's quite interesting to see who are the users of STAN and what kind of other activities you have around STAN.
Yes, of course. First of all, what you can do is you can go to our website. Sorry. Okay, so what you have to do to use STAN is to register here once on the right side. And if you have been registered, you get an email with your that you have to activate your account, and afterwards you can log in here. I will do this. And if you have logged in, you have access to our download section where you can first of all download the software itself. So here's also something available that is an alternative calculation algorithm that you can use in STAN. Unfortunately, not for free. It's a commercial version, but anyway. So if you're computing larger models, I would recommend this commercial version. I think more information about this can be given by Jukka because he's using this algorithm. And what is important is that we have here a database of Stan files that is pretty nice to look at. So each of you, if you are working in a project and you have, let's say, a publication afterwards that is in relation to a Stan model, I invite you to upload this Stan model afterwards to our website. So you can decide to upload it, and what the users can see then is some kind of a preview picture, the description, what the picture is going, what a model is about. And the users can download these models directly here on our website, or, and that's I think the most important thing, you can directly access this database from the Stan user interface. Sorry, I have to. So here you can, sorry, I switched to English version of Stan. Okay, so here you have something that's a web toolbar, and you can log in here with the same data that you have used during registration. If you are logged in, you see here your name, and then you can access this database by clicking this load file from Stan portal button. And here you see a list of all the models that have been uploaded. You will not see all of them because normally when people upload a model, it has status none. That means they are still working on this model and they do not want to have it released or published. But as soon as you have finished your model and say, okay, now it's ready to be released, then you can send me then you can change the status. I get an email notification that you want to release your model, and I will have a small look at it if it fulfills the requirements from my side, and then I will release it, and then other people can use it. And it's pretty nice because whenever you have one of these models here, you can double click on it, and then it is opened. Okay, that's a nice one. Of course, it's not a material flow model, but more or less art done with Stan. And you can use this model and the data that is inside of this model for your own work on your own projects. Okay, any other questions? I hope you enjoy Stan during your exercises. And yeah, that's it. Greetings from Austria. Bye.
Thanks.